Let's start. Yes, so welcome everyone. Good evening. Myself Siddhesh Adavade, and I'll be your speaker for today's boot camp. So about myself, I'm a research associate at Elite Techno Groups, and we're an edtech company. And we're into upskilling students so they're ready for the industry. And a bit about myself is I've had experience in the CAD industry, in the manufacturing, additive manufacturing industry, and I've also done some projects on electric vehicles. So that's about me, and I'm really happy today. I'm talking about this association between RV College of Engineering and Elite Techno Groups, and it's thanks to Chandra Kumar sir taking up this initiative into seeing guiding the students and seeing them that they are getting that extra skills here and there. So thank you, sir, and welcome all the mechanical engineering students of RV College of Engineering. So before we start with our today's session, Chandra Kumar sir, if you have any words to few words to speak.
Yes, sir. Yeah, I can see some RVCNs on the call. So, yeah, good evening, one and all, and thanks ETG for this initiative. And as far as I know, ETG has been conducting these initiatives, and most of the speakers are industry experts, and they are into the cutting edge technologies, electric vehicles,
Right.
CFD, etc. So it will be of great use to students. I request and advise students to ask questions.
Yeah.
And also there will be many more events in the future, and also there will be some internships, etc., which are being conducted by ETG, so that students can get into the core companies. The skills will be upgraded, and you can explore the programs, and you can interact with them though, so that you can take up some good projects in the future, and it will help a long way in your career. So that is what I just wanted to convey to students. And okay, you be interactive and try to learn as much as you can. Happy learning. Thanks for this opportunity. Bye.
Yeah.
Thank you.
Thank you, sir. And yeah, as said, feel free to ask any kind of questions. It could be not just on the topic we're discussing. It could be something else about engineering or something else. So yeah, let's start with our session today, which is on compliant mechanism. So before we start with exactly the topic, has anyone ever heard about this topic before, or what sparked your interest in this topic? You heard about like, okay, compliant mechanisms. Have you heard about this? If anyone could answer this. Yeah, just go ahead, unmute yourself, and you can answer this.
I think this had come from 3D printing.
Yeah. Okay. So, have you heard about this, or you just heard about, okay, it's something related to 3D printing, right?
Yeah, somehow like I've heard of it. Like when 3D printing came into existence, so most of the machines that they can be made of a single part only. All the parts are like, totally made in the printer.
Okay. Yes, Ayush, that's a great answer because it's very closely related to 3D printing, and it's something that is we're not actually tapping into, and we definitely should tap into if you're a mechanical engineering student, especially. And this is something we could learn from and implement it somewhere or another year way in our own projects and our own work. So let's also first see what is exactly a mechanism. So if you've heard, if you've read the definition of mechanism in simple words, it's basically a part of components or subsystems. We take it and we make a system, bigger system out of it that works in cohesion to perform a certain task exactly. Okay. So if you take a real life example, this kind of pen, right? So it's just a very simple mechanism. You tap it on the top, and because of the spring motion, and there's two kinds of slots there. So because of it, the pen comes down, and you can write with it. And when you're done, you can tap again, and it goes back in, right? So that's a very simple kind of mechanism, you can say, where you were using some kind of spring to actuate and then take it back the refit. Then let's look at exactly what compliant mechanism is. That is, mechanism. Okay, we fine, we get it. Some kinds of parts and some kind of mechanism is used. There are joints involved in it. There is motion transfer involved. So this like a scientific explanation or scientific definition of it. So all this is rigid mechanism, you can say, because all this is rigid, and only with the help of some kind of joints and links you can move this and get certain tasks done. Now, what compliant mechanisms do different is they have flexible members instead of movable joints. And as you can see, the example given here, this is just like a type of gripper, you can say. And if you look at it properly, you might see it's taken inspiration from something else. We have, those wire cutters or those grippers, wire grippers. It looks little similar to that, but it's changed a few, dimensions here and there, and then you get a construction like this. So just have a good look at it. And if someone could answer, how many joints are currently, like how many flexible joints are there currently in that in this part, in this component?
Four.
Yes, you're one off. It's actually it's three. So as you can see, this is like it's like a triangular shape, and all the three corners are like flexible joints, and this is just like a kind of lever or stopping mechanism that they're using. And as you can see, how little of a force they're using is just one finger they're pressing like this, but the force at the end of the gripper is enough to break a you can take a chalk and you can keep it there, and it could break easily. Even if you like keep your finger in there, it could cause severe damage. Just you're doing small, you're putting small pressure with one finger here, and you could seriously damage someone with this kind of output. So very simple mechanism, as you can see, and there's lots of applications of this if you look at. So moving forward, let's look at some daily life applications that compliant mechanisms all around us that we use and we don't realize. Okay, these are compliant mechanisms. So first one, you can see this is like a paper clip or a clip to hold some kind of paper or something else. So this is a metal, and you're using a wire, and it's a very simple mechanism to hold something. Other than that, you might have also seen the same paper clip made the same like a clip made from just wire. Okay, no kind of metal part is used. It we used to have this for to hook up clothes to drying. So that is a good example, daily life example or application of compliant mechanisms. And your bendable straws, right? So those have some kind of a type of architecture where you're able to bend them, or you can contract them or expand them. So that is also a compliant mechanism. It's made from just one part, and it's flexible in a way. Then the third one here is by BUI, which is a company who has done lots of research into compliant mechanisms. And you can, after this boot camp, you can go and actually check out the page, and it's very insightful if you go there. So here also they've given like a switch just made of one part. You can 3D print this switch exactly, and it might not like look like a normal switch right now, but with some alterations you could get the dimensions correct and use it as an actual switch in your home, right? So if you have you ever looked at a switch? Have you anyone has opened a switch before in your switchboard at your home? Anyone done that before? Just your normal light switch. Have you opened it and checked what is in there exactly? If anyone could say. Okay, no issue. So when you go and open it, just make sure everything, your tripper is turned off, and then you open it. And you'll see there's lots of small parts, there's nuts, I mean, there's screws, there's springs, and all these things. So instead of using like five, six different components, and then you have to look into assembly of it, you just can 3D print this one mechanism, right? And that also will get into how manufacturing gets super easy, and there's portability and all kinds of stuff then get included. Then our fourth example is the buckle. So this was invented back in the 20th century, in I think 1980s, and from then till now, it's never had any kind of competition. This is the best kind of buckle you can get out there. There's no competition. It's just such a simple mechanism. If you see, there's no complex design involved. Because we always, if you are a mechanical engineer and you're into designing things, you always think, okay, something better design is definitely something that is also more complicated to make. But this is such a simple mechanism, and it's the best of performance or output that you can get from such a simple mechanism. So this is also an example of compliant mechanism, flexible movement. Because of it, the locking mechanism happens. Then your nail cutter. Okay. So, okay, here there are like 2, 3 different parts here, but this also people have found a way to make it from just one single part, just 3D print it, the whole mechanism of a nail clipper. People have done it, and you can go on YouTube and check this out. And all the files also will be available, readily, where you can see just using one part, by using a 3D printer, you can print the whole thing, and you can use it as an actual nail clipper. So those are some daily life applications you'll see for the compliant mechanisms. Okay. Then, yeah. So we'll come to some advanced mechanisms now. So first one, as you can see, this is like a wristwatch, and a kind of very flexible thin metal mechanism is being used to rotate the gear in between this gray colored gear. It's using to according to the time input, it's moving the gear slowly. So there, small parts, you can use this compliant mechanism. You can 3D print actually these kinds of small things, which are really difficult if you try to do it with a subtractive manufacturing. So anyone here could tell me what is the difference between subtractive and additive manufacturing? Guys, come on. I need you to be more active here.
Subtractive manufacturing means machining, and additive manufacturing means welding, means adding material to it.
Okay. Yeah, good answer. Yes, so subtractive manufacturing means you're taking some kind of material and you're chopping it down, and you're removing some part of it, the material out of it, and then you get the final product. So that's a very long and costly procedure sometimes when you're trying to get this kind of accuracy and such small component. So there you can use additive manufacturing, which is the smaller the component, the easier it becomes. You just need to have little bit of precision in that machine. So this is where additive manufacturing really shines. And the geniuses that use this technology and who have come up with this are also trying to implement same kind of mechanism at a microscopic level. If you can imagine how difficult it would be to actually make microscopic mechanisms like this, but somehow they're doing it, and it's really wonderful, and you are left curious how exactly to do that. Then the second one here, if you see, this guy is moving these two rotors, two gear mechanisms, and the part in between is rotating. So that whole thing is made out of titanium. Okay, I just want you to imagine it. It's made out of titanium. It's one of the toughest metals and strongest metals found on Earth. and somehow with just little force of the finger is able to twist it. Okay, so that is also great example of compliant mechanism. And anyone can guess where this is used exactly? Just a guess. Anyone? Come on, just guess where this is used.
So can you repeat the question?
I want you guys to tell me where do you think this kind of mechanism is being used? On your right, top right. What is the real life application of this kind of mechanism? Which sector do you think?
I'm not able to understand the mechanism.
Okay, do you want me to repeat the question?
No, sir. The mechanisms are like what
Okay,
is going on
okay.
in this?
See, what is happening is there are these two gear kind of mechanisms, right? On your left and on your right. Okay. So whenever the person is giving some input, okay, clockwise or counterclockwise, the mechanism in between, the center plate that you're seeing, the circular plate, is tilting in some way here or there, right? Okay. So that tilting mechanism is being used somewhere actually in real life. And here the material that is bending is titanium. If you've ever taken I don't know if you've ever had a chance to have titanium, but it's very strong and you can't really bend it like that. But somehow they have designed it in a way that it bends. Yeah, and this is all 3D printed also. Okay, so just what do you think? Where is this mechanism actually being used in real life? Which kind of sector? Automotive sector, shipbuilding, or somewhere else, biomedical? Okay, automobile. Someone said automobile. Anyone else? Come on, just guess it. You don't have to be correct. Okay, no issues. So this
In
is
watches,
okay in watches. No, the first one was being used in watches. This is not used in watches. Good answer though. Good attempt. I'm glad that some of you are actually thinking and putting thoughts into it. So this is actually used in satellites. Okay, the mechanism that you see is the mechanism that is used to rotate or angle the boosters of the satellite, to give it certain direction. So what used to happen, right, at NASA, this problem was that the satellites needed two boosters to direction itself on a particular trajectory. Now, because of this simple mechanism, first advantage was, since it was 3D printed, it was very light, and that is what actually you need in a satellite. It should be very light. Second, it's very easy. You just have to attach two motors there, and you'll be able to give the direction to the booster. Not a very complex thing you have to design where lots of moving mechanisms are required, and lots of parts are also not required for this. So because of that, from two boosters, only now one booster is required for those satellites. And this is the kind of things that compliant mechanisms are able to achieve, right? So that is also a big thing. You're cutting the cost down from two boosters to one booster. That's lots of money you're saving for your organization. So that's a big thing, right? Then moving on to the next one, you can see they're using it as a door hatch. So if you see closely, it's not thermocol or rubber like material. It's actually very solid plastic. Okay, it's very hard plastic, and still it moves in a way you feel like it's kind of a thermocoly or rubbery type of material. So in such a way also we could use a plastic, a very hard material, and we can bend it in for some kind of application. Then there's also this one, also a kind of gripper for a cylindrical surfaces. So or any kind of any shape of cylindrical surface you can lift with it. Okay, even like squarish surface you can lift with it. Then last one is like a it's trying to imitate a natural, very natural, like a cat or a dog's feet movement. Okay, so this is also a very good mechanism if you're going into research, all this flexible joints and trying to replicate the nature. Okay, so let's look at some more examples, because we can't just stop at that. We need to go further and further and look at exactly how they're being implemented. So let's look at a field actually, that is robotics, and how its compliant mechanisms is changing the field of robotics. So the first one you can see, it's the legs, they're moving with the input of air. Air is blown into the legs, and because of that, they move. But they're also made from just one material, just one component, 3D printed it, and then they have attached airflow tubes, and then with certain actuations of the airflow, they're able to, actually independently move each limb. Now, this is also something that could be used to send rovers on different kinds of planets and moons, and you can use this kind of mechanism there. And it's very flexible, and right now it might not look that advanced, or it could look like, okay, this will get stuck somewhere, but slowly it gets better and better, and one day we'll have like a amazing mechanism that could roam around anywhere with just use of simple plastics, 3D manufactured plastics and airflow. Then the second one, the robotic arm, as you can see, it's also just made from one mechanism, and a string kind of mechanism is used to, grip it and pull it. And also there's then sensors and all these things are also involved, but the base of a compliant mechanism remains the same. Then also the bird, okay, the bird animation. So this is actually used by Disney to replicate, to take a reference, actually how nature's, if you want, they wanted to animate like a bird, okay, fully see actually how it works. So they tried to get a mechanism into it, and then they modeled the 3D graphical board around this mechanism, so it could imitate the natural movements of an actual board. And because of it, lots of Disney's movement, if you see those films, look very natural, right? It's not like fidgety and choppy. It's very natural movement. So they actually invest into research of all these things. They're not just sitting there and animating. They're actually researching into all of this. So it's a great thing. A company like Disney is into actually technology, right? Then the last one is this one is like just blows my mind how they're able to take a kind of plastic and bend it like it's some kind of cloth or some kind of rubber, right? And this was also just made by some kind of design techniques by incorporating 3D printing as well. And then you could have lots of fun with this and do lots of research with this, lots of research applications for this, right? So overall, I hope you understand the amazing things you can actually achieve with compliant mechanisms. Okay, so any doubts in this so far? Any kind of mechanism you didn't understand? Okay, so no doubts. Cool. Then now let's look at advantages of compliant mechanisms over simple normal mechanisms. So I've just mentioned here three of them, but there's like multiple advantages for this. So the first one is price of production. Now, why this? We'll take an example of this same gripper. Okay, so why this mechanism is cheaper than the the wire cutter or the gripper tool? So for that, lots of you're cutting down the requirement of all these different parts that need to be manufactured differently, and then you have to put someone to assemble it. So lots of money goes there, and although all those other parts might be made from subtractive kind of manufacturing, and here you could just have like a 3D printer that goes on printing all this layer by layer, and you just go on chopping it. You have lots of parts like just simply, and that is also a point, that is ease of manufacturing. Very simple to manufacture this component, because most of them just have one part. They can be made from just one part. You don't have to even look for assembly. Just you have to 3D print it, and that's it. It's ready to go. It's ready to work. So inexpensive and ease of manufacturing, very good things, uh, very great advantages. And then the last one, I think, which is very important, is proportions and portability. So let's say the person holding here, the mechanism, it's like the size of a hand. Okay. But what if I just, did it at the half size, just shrinked it on your software, again, then 3D printed it, and it would work the same, right? It wouldn't work any kind of different unless you go very small, and then the plastics might not be able to bend that much. But if you see just the same thing, we have to just change the dimensions and then print it again, and then manufacture it again, and it's then becomes portable, very portable, and you can play with the proportions according to your needs, how much the force is required. Accordingly, you'll increase or decrease the size, and you'll have the product made. So like this, these are just three advantages, and I'd like to ask you, let's discuss about what could be one more advantage of this kind of mechanism. Just one or two more advantages from your side. What do you think? Come on, engineers. Just one, two advantages. What do you think? Just name a few. It could be wrong. It's okay.
No chemical reaction with the external environment.
Yes, good point. You can make the kind of choose a certain material according to the application that it's being used. Maybe you're using it under some chemical. You're using it, and the environment contains some kind of chemicals, and you could make it out of a material that is resistant to that chemical. Right? Great point. Yes. Who was that? Okay, whose suggestion was that? Who was that? Okay. Anyone else? Any kind of advantage?
Zero maintenance.
Ease of maintenance, yes, right. Lots of parts are not there, so there's no wearing of parts, so no kind of maintenance is there. And even if like maintenance will be there, if you think about it, manufacturing all those parts and then assembling it in a normal gripper, and the cost of manufacturing of this, it's just few rupees, I think, right? So even if it gets 1-2 years, it gets worn out, you can simply make another, and it will still be cheaper than the other part, right? Great point, Ayaz. Okay, then we'll move forward. So those were some great points, and that is, I think, leading to materials, which we'll get on further in the presentation. And let's look at how you could actually design one. Now, designing one is not that easy, and you require lots of years of research, but this is a simple case study for you to understand the process that goes behind designing one, right? So let's say I have to perform a task where the arm or the mechanism has to go in this kind of shape, a half oval kind of shape, right? And for that, I'll devise a mechanism with joints, right? So a kind of joint that goes in follows a certain kind of trajectory. That is my output that I require. Now with joints, again, this is the normal mechanism. There's lots of complications, and now we have to turn it into a compliant mechanism. So for what first we'll do, motion tracking is done. Okay, what is your exact output that you need, that you have done? You've made a mechanism with joints and other things. Now the second part is collisions avoidance. So you'll see exactly where the issues could be there, all these cycles. Because let's say your joint is, your mechanism is gonna run for like 10,000 cycles. So there might be things that could collide with each other. Joints and members could not function properly, and you could have certain wrong scenarios, like the one given in the red line. It could go, somewhere that is not the required output. So for that, what we'll do, we'll add some flexible joints. Okay. So wherever there is like collision, we'll try to add some flexibility into it. And for that, as you can see, the joints don't require to be that thick, or that much, don't have to be that big dimension. We could have like very flexible and thin joints made out of hard materials, or a kind of material that is very that has lots of strength but is also flexible. And lots of plastics nowadays are very good at that. So we have done collision avoidance. Now there is still one issue that could be when you're trying to make this thin and flexible joints with plastics over 10,000 cycles. They could also break, right? Because they're very thin, and plastics could sometimes break with the fatigue. So we have to actually select the right kind of material, and maybe we will have to increase the size or change some dimensions here and there. In the third image, you can see some of those dimensions are a bit, the mechanism is a bit moved here, twisted. It's given little different shape, and the links are now, the flexible links are a bit longer than before. So that in this case, that cures this problem of failure. Okay, so failure won't happen for a long time. And the final thing is torque optimization. So according to your need, right, you have to optimize what kind of force you'll be putting into it to get this kind of output. So even if we look into a gripper, we're asserting a force, right? And we'll have to exactly calculate how much we need for the output, and accordingly we'll make a mechanism where that kind of motion, the force multiplication or division happens, right? So we have to study that and tune it according to that. And once we have done that, we'll have a compliant mechanism which is flexible, and it could be manufactured within just 1-2 components or parts. So this is just like a case study. And this is also, if you can see, it's done in just one axis. Okay, this is just on one plane. And you could incorporate then 2 or 3 planes and make it a 3D motion, just like they've done for the wings of the bird that flaps. So as you can see, there are these thin flexible links and joints that make this kind of flexible and very fluid motion happen. Okay, so that's how you could start into get look, if you have to design a kind of compliant mechanism, just take any kind of mechanism and look what are the different joints and where is it actuating and what is its purpose exactly, and can you replace it with something flexible, right? And then you have to see if it's if there are any kind of collision because it's flexible, and could it break, or what could I do to not make it break, and how much force is required then, and what is the output that I get. So all these things you have to see for making a compliant mechanism. Then let's look at now 3D printing this mechanism. Let's say we have designed a kind of mechanism, and now you have to 3D print it. So first you look at materials, right? So what exactly, according to your needs, what materials you're selecting, right? So in plastics, we have given some 4 materials, and we'll also look at some metals that are used. In plastic, there is a PLA, which is one of the most used, the PLA and the ABS material. 2 of the most used materials when it comes to 3D printing is both plastics. and PLA is a little eco-friendly, and whereas ABS is a little toxic. So you have to have a controlled environment for it. But both of these materials are good, and they are used mainly for DIY projects. So the normal 3D printer, the FDM kind, will go into 3D printers as well. But the FDM, the normal 3D printers, both these materials are usually used. Then there is something called as PVA. Okay. So very fancy names all of these have, but we just use the short forms, very simple. Let's not make it complicated. So PVA is a dissolvable kind of plastic. So that is used for support material. So what happens is, maybe you sometimes have to make a very complex thing, but it's like floating in the air. So you can't make a part which is like floating directly in the air, because 3D printers can print in the air. So you have to provide some kind of attachment or some kind of support to it, support structures. And those support structures, then after we don't need it, right? Once it's all 3D printing is done, then we can have those structures removed, or they could be dissolved. So this plastic is used there. So we could, this is dissolvable with water or some other kind of solution, and we could dissolve it, and we'll have the final product, finished product. And then the last one is PC, polycarbonate. So this is a more high quality material that is a little bit more expensive, but the output is also that much better. So this is a little more has a little more strength in terms of plastics. Then also there are metals. Now there's stainless steel, bronze, gold, nickel, aluminum, titanium. All these metals are also available for 3D printing. Or sometimes what happens is these materials are mixed with kind of plastic, and it's kind of a mixture of both of them, a polymer kind of thing, and that is used directly. Okay, so that becomes cheaper, but it still has lots of good properties of that metal. So that's how it's done. Otherwise, directly the pure material, the metals are also used. Now you could go into this further and research all kinds of materials. There are lots of kinds of materials, lots of in-betweens as well. According to your application, you could choose them. Then about 3D printers. Okay, you've selected, you've designed your kind of compliant mechanism. You've selected a material for it, and by doing all research, you have selected not just randomly. And then you also, again, by research, doing research, select a kind of 3D printer. Now we have 4 main kinds of 3D printing technologies. There's more, but these are the more prominent, and I think you might have heard about this, right? So, or you might have seen this, but not known their name. Okay. So first one is FDM, fused deposition modeling. And this is a very, DIY print kind of 3D printer. You will find it at lots of places. It's now very cheap. It used to be costly, but it's now very cheap. You can buy one for yourself. And the price of, I think, an Xbox, I think cheaper than an Xbox, you can buy one and start making your own 3D printed projects. And it's very fascinating, actually. If you step into the world of 3D printing and manufacturing, it's very easy. You just you'll require just 1 week of learning, and you'll be good at it, and then you can make lots of fun projects with it. Then fuse deposition modeling. Here you have a kind of filament. Okay, the filament is melted, and it goes through a nozzle, and layer by layer, it prints the model. And then you can remove it and whatever you want to do it. So this is a very simple way to 3D print. Then we come to digital light processing, DLP. And there is something called a stereolithography, SLA. Now if you see, both these methods look very similar, right? In both you have kind of a tray of solution or chemical, and there is a arm above, and it's holding the project, whatever component you're creating, and then it slowly forms. Now the only difference between digital light processing, DLP, and SLA is one uses the digital light processing uses this UV laser. I'm sorry, UV light, and the SLA uses the UV laser. So how these both are different is, there is a tray in which you have a solution for some kind of plasticky material. There is a polymer solution, liquid based, and then in the DLP, what happens is it scans like a like a Xerox machine. So the UV light is shown on it, and each time it flashes, each one layer starts forming, and slowly the arms pulls it up slowly, and each one layer is getting built down there. And here, as you can see, the structures are required to give it some kind of support. It's kind of like a goggle frame is being built here, and structure is required to support it. So that is being done in DLP, and in stereolithography, UV laser is being used. Now, how laser is different from UV light is the laser is actually tracing it. It's not like a flash of light. It's actually going through all those. It's like a FDM where you're making layer by layer, but it's now upside down, and it's like a laser, and it's using the liquid solution to make it. Excuse me. Yeah. Okay. So only this kind of difference. One uses UV light, one uses UV laser, and SLA is like a older technique, and DLP is a more recent technique. And SLA is little cheaper, DLP is little more costlier, but in DLP you get more high level of detail. Then there is something called as SLM, selective laser melting. So using this, you can build high quality metal parts, fully metal parts, not the mixture kind of plastic and metal, fully metal parts. And these are actually used in production of a lot of lightweight things that are used in airplanes, rockets, satellites, even in automotive industry. If you have heard about this, there was an article, lots of news and buzz around it, that a company made a whole car out of SLM, this 3D printing technique. So lots of all those metal parts for the car that were made by 3D printing actually, right? And because of this, what happened? The car was very light, and it was just around, I think, 900 kilos, or I think 1000 kgs, somewhere between that. And if you know, the usual weight of a normal, supercar is somewhere between 1000 to 2000 kgs. And they made a car around 900 to 1000 kilos. Why was this possible exactly? So in 3D printing, one thing you can do is you can create small pockets inside the material. It need not be a whole metal, right? It could be like a honeycomb structure inside the material. From outside, you might not be able to see, but inside it could be like a very honeycomb material, and it would still have the level of strength that the normal material has, or even better than that. And it's still lighter because inside small, sections, the material is not there. So lots of, weight is saved there. And also then something called as topology optimization comes into play. If you want to write it down, it's also very interesting thing to go and check out and research on it. Topology optimization. It's done using our FEA techniques, where you take a component and you're trying to shave off some weight out of the component, but you are still trying to keep the rigidity and whatever the previous properties were there, but you're trying to shave off some weight. So if you've seen, an example of it could be like a vehicle knuckle. So I don't think you might know about knuckle, but you just go and Just put in this word topology optimization, and you can do research in this. And SLM is a little bit recent and newer technique, and it's very high, high expense, very high expensive method of making 3D printed parts, and that's why it's only used in that high quality applications. So these are the four prime 3D types of 3D printers. There's lots more to talk about these printers, but we have only got a certain amount of time. Maybe in some other boot camp we could just talk about 3D printing and how it's done exactly, what all things you need to consider, and how you could actually make one, make a 3D printed part. Then let's try to wrap things up and look at today's exercise. Okay, so this is something I want you to include it and try and go check it out how it's done, right? So I'll give you a link. Okay, so this is like a Google form link, and you'll in the first part you will receive this part there. Okay, this part file I've given it to you, and you can open it using any kind of CAD software, and you can just see what are the different dimensions. So this is also kind of gripper, where if you just hold it like this and just actuate it with your hand, you can grip whatever is at the mouth of the gripper. So it's also kind of gripper, and you could go check out the dimensions. What are the different dimensions? Okay, here also there are lots of flexible joints. Okay, here there is a joint. This is also a joint that moves and come down. This is also a joint. So go and check out what are the different dimensions, how thin the joint should be to be flexible. And then once you've gone through the part and the dimensions, then the activity starts and the exercise starts. That is, you have to for I'll share one more sheet with you. So this is what this is what will be asked in the Google form. Everyone can see this sheet?
Yes, sir.
Okay. So this is your basic exercise. So what you have to do is, first you have to see what are your local manufacturers, 3D manufacturers around you. Okay, within maybe 50 to 100 kilometers of range. What are there could be lots of them, or there could be none. So you could keep expanding your range, and you have to find two such manufacturers. Just name that down where the location is. Get the contact actually, or it could be their mail or their phone number or even the website URL, and then through that you will receive their email. And I've actually went into an exhibition of this 3D printing technology, and these guys are very into helping you. So if you just ask them, you call them, you have to ask, okay, what does a company do, what kind of 3D printers they have, what kind of materials they have, and they'll gladly answer all your questions. And you then tell them basically, I have certain project, I have to print a part, right? And they'll give you all the details. Okay, what kind of 3D printers they have, what kind of materials they use. And if you just give them the 3D part, okay, the CAD part, they will tell you how much it will cost you to make that part. Okay, they will give you a quote, okay, on if you have to manufacture like hundreds of these, so what is the cost exactly, or you have to manufacture 10 of these. So you just let them know that I have this project, I have to 3D manufacture this part, and then they'll give you a quote, okay, how much amount will be required to manufacture this, and you just divide it by the number of components they're saying, and you just find out the price of one of those component. Okay, just one, making one of those gripper, and you note it here. So this is in a way trying to get you to into 3D manufacturers around you. And actually what happens is, we think this is a recent technology, so it's very costly and like that. So it's not costly at all. And honestly, you could buy a 3D printer yourself and print those things, and it's a very fun process. And even I've done this. So definitely something you should get into. And additive manufacturing itself is a, you start thinking, wow, we've come so far in terms of technology, and we are able to build this kind of complex things by just giving some commands, just uploading a CAD model, and rest of it the machine figure out itself, right? And it uses some state of the art technology to perform all these things, and then you have it just like that. Just like a microwave, you put food in and you get hot food. So something like that. So go through this. Genuinely call these guys, and they'll be glad to answer all your questions and give you all the details required. Just two of the manufacturers, local buyer manufacturers, you can go on the website and let them know what you're trying to do and get a quote. Okay. And then what you do is, once you have two of them, you select one out of them. Okay, so one could say we use FDM process. One could say we use some kind of laser process. So if this process is something that we have not discussed today, just ask them, okay, what kind of technique is it, right? How do you do it? What is it exactly? Even if they talk about a technique that we have discussed today, just yeah. Okay. Yes. So just ask them what kind of techniques they use, and just select one out of those two manufacturers. Okay. And once you select one out of those two, okay, you'll have two options. One does FDM, one does some kind of other thing. You select one out of them according to your reasoning. Okay, just state down reasoning. Okay, this one is giving me cheaper price, so I've selected this because the application is so and so. So this material is okay for it, and this is a fair enough price. So I'll go into. I'll choose this one instead of this one. We don't actually have to give them the money and actually tell them to print it, but you just state the reasoning there. Okay. So all of these things are mentioned in the Google form. There are 3 pages. First, you will enter your details. Second, in the first one, you'll also get the 3D link of the 3D part. Okay. Then you enter your detail, do all your research, enter your details. In the second and third page, you fill all of these things up. Okay. And I think in the fourth page, you have the reasoning selection and reasoning part. Okay. So once you do all this, then we'll provide you, once you do all this and then hit submit, in within 24 hours, we'll go through all your submissions. 24 to 48 hours, we'll go through all your submissions, and then according to your work, for each submission, we'll provide you with a certificate. Okay, for this bootcamp. So any questions about this exercise? Anyone? I'll paste the link here for the assignment. Okay. So the link has been pasted in the chat box. Okay, once you do this assignment and submit it, we'll send you the certificates. Okay. Anyone has any doubts with the assignment or even with the bootcamp? We will first look at the assignment first. Okay. Anyone has doubt with the assignment? How to do it or what exactly to do if you have missed a point? Or about the certificate?
Can we see like what other students build in the manufacturer's name? Like if we want to know about like where the manufacturers are. Like, I don't know anyone around my locality.
Okay. So, yes, good doubt, Ayush. Exactly how we'll get in touch with these manufacturers. So one thing, even what I did was, so you just go on Google and type 3D, 3D printing manufacturers around me or in your particular area, and name that district maybe. Okay. And the other thing is the India Mart website. Okay. So there also you'll find lots of contacts. They've given directly contacts of those manufacturers there, and there you could call them and you just ask them directly. Okay, don't feel shy. These guys are very helpful. Trust me, I've spoken to them, and because see, this is their business. Okay, they want to actually make the components and sell it to you. So they'll tell you everything. Don't feel like, okay, I'm not actually going to buy it. I'm not actually going to give him an order. So maybe this. So that is not there. Don't worry about it. You just tell them we are working on a project, and I would like to know all these details. Okay, on you could check on India Mart, and you could also just Google it. You'll find it. There's lots of small manufacturers in today's day. You'll find. And one more thing you could also do if you want to go offline is there are in all cities and districts there are certain sectors that are just into manufacturing. You call them manufacturing sector. So just all the go downs and plants are there for manufacturing. There also you'll find these kinds of manufacturers there. Okay. So if you, I don't know about Bangalore, how it's there, but yeah, in Mumbai, there was a place called Vasai. So most of the manufacturers were there. So if you ever had to, look for a certain kind of additive manufacturer, you just go there and search around, ask the locals. And just, don't feel shy about asking things. Just this one skill, just, asking will take you so far in your journey as an engineer. Even my personal experience, my first job, I gave the interview for a position, and then that was a different position. And then I saw they also have a posting for another position that was more inclined towards me, what I know. And so I just asked him, okay, I've already gone through an interview, and my interviews has been done. And just as I'm leaving, and I asked them, okay, there's one more position I just saw. Can I apply for that? And they just told me, okay, since anyways you're selected for this, you don't have to get that different interview. Is it directly selected for the the other job? So I was like, okay, that's great. I don't have to give any more interview. So just asking could take you a long way. And as an engineer, I think uh, if you've seen any, even your teachers or mentors or some uh, senior engineer, anywhere they go, any technology related place, they just go around and ask people lots of questions. And that is just the one difference between us beginners and them. So don't feel shy from asking. Okay. Okay. Other than assignment, any questions about our boot camp for today? Has everyone understood what a compliant mechanism is? Basically a flexible machine, right? And maybe now in your final year projects, you might try to implement some kind of flexible mechanism there. Not everything you have to change. Maybe one thing you could change, and that could be a whole separate, one small section of it that you have done certain project, but you have also used a kind of compliant mechanism that, so that could also be a big booster for your final year project. One more thing. Okay. Yes. Thank you, sir. Yeah, I'll send the feedback link. This is the feedback form, and the first one was the assignment. Yeah. Yes. Then before ending it, we talked about the pen mechanism, and this is just an example of how somebody changed the pen mechanism into a compliant mechanism. And I just wonder, if these things even we can think of and make it just such a simple mechanism. It doesn't look very stylish, but it's certainly, good enough to do the job. And all these compliant mechanisms, most of them are taken from a website called Thingiverse. Okay. So I've mentioned lots of references here. You could go and take a screenshot of it, go check them out. Lots of references here. Yeah. And okay, just take a screenshot and I'll go back to the other page. Okay. Yeah. So about talking this pen mechanism, it might look a little hideous right now, but so did the phones. In back in early 2000, we had this chunky phones, and then slowly the design gets updated, and now we have super slim phones. So slowly the compliant mechanisms could also start looking a bit more aesthetic, but right now we just want them to be more application based, right? And maybe you could someday design this, or just have download somebody else's design for this pen. You will find it on the internet on the Thingiverse website, and you could 3D print it yourself, and then maybe carry around this pen for interviews, and maybe the interview will ask you what exactly is this, and then you can go on a tangent and let them know about your knowledge in compliant mechanisms, right? So that could be a great conversation starter for you guys. Okay. So with that, we'll close the session. I hope you have gotten insight about a different way of thinking and different way of designing mechanisms, flexible machines, right? Yeah. So with that, I'll sign off. Thank you for coming here, everyone, and being participating in this, and keep learning and keep exploring. So that's it from me. Chandrakumar sir, any words
Yes,
before? Yeah.
Yeah. Thanks for the session, and maybe you have given your contacts for students to.
Okay. One thing I'll do is I'll drop down my email address. Yeah. So if you want any kind of help with this, you actually want to get into 3D printing itself, I'd be more than happy to help you, and I will look forward to actually how to. If you have any kind of project you want to get 3D printed, we'll definitely look into it. Okay.
Okay. Thank you very much. We will get in touch.
Yeah.
Okay, thank you.
Okay. I've mentioned the email, my email address as well. Please fill the feedback form and do your assignment. And as soon as you submit your assignment within 24 to 48 hours, you will receive your certificates. Okay. Okay. Yes. Yes. Thank you again, Chandrakumar sir, for taking up the initiative. We're looking forward to this association with RV College of Engineering. Thank you, sir.
Thank you, and thank the student for being here. Thank you.
Yeah. Thank you, students as well. Yeah. Okay. Bye then. Bye, guys.
Bye.